All right, good morning, everyone. Today we're gonna go over some proof problems, especially inductions. So let's just get started. Is there any question before we go into the problems? Okay. So the first one is on the number proof. So we want to prove the product of an odd integer and an even integer is always even. I'll just give you guys about 3 minutes to work on this one. Okay, so do we need more time, or does there anyone want to share his approach?
So I just substituted, I wrote the product as x times y, for x is the odd integer, y is the even integer.
Okay, so we can just let's write in a formal proof. We can just set this up. So you want to let x be the odd integer, you said?
Yeah, that's right.
So we're going to use 2k
And then
plus
y.
1.
Mhm.
And we have y as the even.
Yeah, and I was actually wondering, when we write these formal proofs, is it okay to use k for both of those? That doesn't imply that it's the same k, right?
Well, just for safe, yeah, I guess you're right. I can just use another variable. Let's just use 2n and 2n plus 1 and y equals 2m, where both n and m are integers.
Perfect. And then I just substituted that in the product.
Okay, so we start with x times y. And, oops. You're just gonna do the algebra, right?
That's
Just
right.
basically time this. And that's 4mn plus 2m. And we can just take out the 2. And now we can use k by closure, where you have k as an integer as well. And thus you also want to write your conclusion. Thus or therefore, the product of an odd integer and an even integer is always even. And you're done with the proof. And then to be precise, you also want to write down by definition of, let me see where it is. Right here, you also want to write down by definition of odd, and right here by the definition of even, like on your homework and on the quiz. All right, any question on this problem? Yeah, it would be better if we just use different variables to represent the x and y, because otherwise it might be implied that x is actually, y is actually increment 1, or y is just like x plus 1. Okay, so the next one is use induction to prove that for each integer n is greater or equal to 1, n cubed minus n is divisible by 3. So before you get started, think about the 4 steps you need to write down in induction proof. So whenever you're doing a homework problem or like on the quiz, we want to like to see your 4 steps. So anyone want to say like the 4 steps?
I guess I'll just go again. One is prove the base case.
Okay, so base case.
But you start by declaring what your predicate is.
Yeah. So like basically the problem statement. Just restate what you're gonna prove. And then you're gonna show like your base case and what's gonna be the next step. Yeah, I think we have that in the chat. The next one's gonna be the induction hypothesis. And the last step is gonna be inductive steps. All right, I'll just give you guys about 3 minutes to work on this one. I noticed that we have some questions in the chat. Yes, I think are some of the like the basic proofs, like the division theorem, where you have the I'm just going to use x here. You have the formula like this, where your q would be I'm not exactly sure if this is the right notation, but you can use any letters. Where the divergence theorem says, in this case, if your x is even, you just kind of basically utilize like whichever you want. And then in this case, q would be 2, and r would be 0. And the other one would be closure. Okay, so how are we doing on this problem using the induction? So the base case, well, let's start from the problem statement. The base case would just be, we want to prove that our, what are we going to rewrite the n cubed minus n is divisible by 3 for each integer n is greater or equal to 1. If we're going to use the division theorem. Yeah, that's one way. Oops, we can write like this. Or we can just write like n cubed minus n, yeah, equals 3k. Where you have your n is greater or equal to 1. And how are we going to show our base case is true in this case?
I think we just set n to 1.
So we start with n equals 1, and we just kind of substitute that in, which will got 0. And we know that 0 is divisible by 3. And thus we have proved the base case is true. Okay, now we move on to the hypothesis. What's going to be our induction hypothesis? There's actually different ways to set up your hypothesis and have a different kind of inductive steps, but the reason behind them are all like the same. The logic here are all the same. So we can start from assume that P of n minus 1 is true. And we know that Pn minus 1 is n minus 1 cubed minus n minus 1. I'm just going to move this below. All right, and we know that this is equals to, I can just use 3k here, or probably another variable would be better. Let me just say r. Okay. And what do you want to show in the inductive steps? So So what are we trying to do here? So we're trying to use the hypothesis to prove that n cubed minus n is equal to 3k. That's our goal. And the idea behind induction is just to use the whatever you assumed in the hypothesis, and you can just substitute that into your inductive steps, and then to somehow create this. And since we know that we wanted to show that n cubed minus n is equal to 3k, so we must start with n cubed minus 3n. And that has to be equal to something, where you can actually use the one in the hypothesis. Any ideas on this one? So let me write this more clear. So right now we're assuming that P of n minus 1 is true, and I want to prove that Pn is true based on our hypothesis. So right here we have this as our hypothesis, and we're trying to start to show that this is equal to some like 3k. So in this particular problem, it's actually harder to, or like not harder, but just like a little more like complex to use to start from n minus 1 and go up to n. It would be actually, I think that it would be actually easier to go start from n and then go to n plus 1. But it is still like doable. If we just expand this equation here, the hypothesis, we will get n cubed minus, I think that's 3n cubed, n plus 3n, and minus 1. And that's the expansion of the n minus 1 cubed, and minus 1. And this will give you n cubed minus 3n, sorry, this should be n squared, and plus 3n minus 1 minus n and plus 1. And then we know that you can, the minus 1 and plus 1 cancel out. And if I just move the n squared minus n over here and minus n squared plus 3n, sorry, that's n cubed. What do you see here? And this is equal to 3r, as we assumed the hypothesis is true. Like, what do you see like these two steps? That I can actually show that this is true.
Can we move negative 3n squared plus 3n to the other side? And then, so that would be saying that n to the third minus n is equal to that, and then factor out the 3 on that side. And then that would say that's equal to 3 times n squared plus n. So we would be saying it's equal to 3 times the inside of that, which means it's 3 times something, which means it's divisible by 3.
Yeah, I guess, yeah, I see what you mean. So, but I think actually on the left-hand side is the P of n minus 1.
Oh, right.
Yeah, so, but it's like the same idea. So if you just think about we know this equation right here is equal to 3r, and we can factor this 3 and this 3 out. And the only thing we're missing here is like this 3. So the term n squared minus n must be divisible by 3 in order to make this whole equation equals to 3r. So let me just write next page. So we have Pn minus 1 equals to n squared minus n, and what is the term? N minus 3n squared and plus 3n. And we know this is equal to 3r. And that is by our hypothesis.
Yo, Jack, do you start your job soon?
I get my stuff Monday, so training or paid training next week.
Is there someone want to?
Are they just retraining you?
Yeah, so I'm literally learning nothing new, so I'm just gonna be, I don't know, jacking off for like 10 hours a day.
Watch this. The penny's gonna go in the pan.
Hey dude,
Oh.
you're
It's
unmuted.
refreshing when I learned, like, I told the guy, like, yeah, I worked here a year, everything. Oh, my consciousness process changed.
Hey, Jack's friend, you're not muted.
Okay. All right. So we know that this is equal to 3r. And since these two terms, we know these two terms are all divisible by 3. And the only way to make this whole equation is divisible by 3 is that this term, n squared, n cubed minus n, is also divisible by 3, which is equal to something like 3k. Any question on this part that we're trying to show that Pn is true based on Pn minus 1?
Yeah. So is it equivalent to rearrange it and then factor out the 3 and then say that that is divisible by 3?
Mm-hmm. Yep. So we can actually do like I said, the way you're trying to show that P of n is true based on P of n minus 1 is true is kind of like more complex compared to if you just assume Pn is true and then you show Pn plus 1. We can just do this real quick. So if you have Pn, if you have assumed Pn is true, which you know that n cubed minus n is equal to 3k, where k is some integer. And then you just kind of start with like the regular procedure. Start with P of n plus 1. You just substitute n plus 1 into it. And then like always, you just try to expand this first. And this should give you n cubed plus, I guess it's 3n squared and plus 3n and plus 1 and minus n and minus 1. And you can cancel the plus 1 and minus 1. And again, you can move the n squared minus n and plus 3n squared plus 3n. But right now, you can just directly use the fact that our hypothesis is true. Just by directly substitute that in, we know that n cubed minus n is just Pn. And that is equal to 3k. And then just by closure. Oops. This is probably equal to some number, 3q. So this way is actually more direct, I would say. You could just use the equation in the hypothesis directly.
I have a question.
Mm-hmm.
In the n-1 example, did
Yep.
we even need to get to the last step, or did we kind of just prove it in the third step?
You mean like in the hypothesis?
Yeah.
Well, yeah, you can do the expansion and the calculation in the in your hypothesis steps. But you also want to kind of explain in your inductive steps, like how you get to n squared minus n is equal to 3k, just kind of like give a conclusion. If you were trying to use the n plus 1, n minus 1 to n.
Are there any
Okay.
steps in the inductive steps that you'd want us to list other than the closure property?
The closure is definitely one of them. Also, sometimes you're gonna use by the divergence theorem, like right here in the problem statement, and also like in the hypothesis here, like why we know that P of n minus 1 is equal to 3r, and that's by the divergence theorem.
I think there was
Yes.
a Piazza post that said if you are using like any distributive functions or commutative actions, you should write those also.
In the proofs, or like in the logic, like the
I'm pretty
Boolean-
sure it was in the proofs.
Okay. Yeah. And then yes. I guess that's also needed. But I think the key parts we are looking for most are going to be the divergence theorem and by closure. And just be careful with the variables you're using. We don't want like use like all the same variables like again and again like in the same question. Otherwise it would be like kind of confusing. If you have like 3k here and you also like end up getting like 3k. If you have like 3k in the hypothesis, you also end up getting like P of n plus 1 is also equal to 3k. That would be confusing. Just use another variable. Okay. Any more questions on this one? Great. Can move on to the next one. All right. The next one didn't actually say which proof you're gonna use. But basically, so far, the proof techniques we have encountered are like the direct proofs, like the one we did the first example, where you want to show that the product of even and odd is always even, and that's like a direct proof. You're just gonna work on the proofs. And the other one would be just proof by cases, and also induction. So just think about what are you going to use in this one, and I'll give I will give you guys about 3 minutes.
I have another question. Do you suggest that we just start with P of n and then do P of n plus 1, or should we? It doesn't matter really.
You mean for the in general for the induction proofs?
Yeah.
It actually doesn't actually matter. Like, I personally prefer to assume like Pn is true and then just go one up. But like it's actually the same. Like even you can do like P plus 10. Like you can assume like n plus 10 is true and then show that n plus 11 is true. That also works by just a lot of like algebra things going on. So yeah. like just basically like personal preference.
All right, thanks.
It's just sometimes I feel like when you are using like the n-1, like we are like involving like the minus sign, like the subtraction, it probably will cause like more works to do compared to the plus. But that's like still kind of depends on the problem. Okay, so just to save some time, we're gonna use proof by cases in this problem. So anyone use proof by cases can share their solutions or take a shot or just type in the chat.
I used proof by cases, and I started with case 1 where n is equal to 3k plus 1, k being some integer. Then I substituted it into n squared plus 2 and used expanded it and used closure properties to prove that it is in fact divisible by 3, n squared plus 2.
Okay.
And then did the same with n equals 3k plus 2.
Okay, so we have two cases here. And you're absolutely right. That's basically the idea. We're gonna work on this problem. Yep, so we have our first case gonna be, so why, before we actually get started the computation, why we're gonna have two cases, but not like 3 cases or 4?
Because the division theorem states that the remainder must be less than the dividend, or I'm sorry, less than the, what is it, the divisor.
Yep. So right here it says if n is not divisible by 3. That's why the only cases where n is not divisible by 3, which one of them is when n has a remainder as 1 or has a remainder as 2. If this problem changed to if n is not divisible by 5, then how many cases you should have? Yep, you should have 4 cases. All right, so we started case 1 by letting n equals to 3k plus 1, and just like always, we just want to first substitute that in. And everything after that should be pretty straightforward. And now you can take out the 3 to actually makes it look like it is divisible by 3. Oops, that should be 2. And that's plus 1. All right. And you're done with the case 1. And case 2 should have like similar steps. I'm just going to write on the next page. What is it, like n cubed? N squared plus 2. So we have, if we just substitute that in, so I'm going to work here. I'm going to take the 3 out. And leave whatever is inside, and then just by closure and use another variable. It's got 3q. All right, and you're done with the proof.
Is there anything in particular we should put at the end of the proof when we're using cases like, yeah, I can't think of an example, but.
Even like a conclusion or something, just say like it's end of the proof.
Yeah, do we need to mention anything about the fact that we proved all the cases for, or something like that? I don't know.
Usually you're gonna have like just put like a sentence or two below each cases, like for case 1. After this, you can just say in this case, when n is equal to 3k plus 1, the n squared plus 2 is divisible by 3. The similar for case 2. And then therefore, like you can write like a overall conclusion saying that if n is not divisible by 3, then n squared plus 2 is divisible by 3, based on our 2 cases.
Okay, thanks.
That's all I mean. Mm-hmm.
Quick question. So when we said that to say it's not divisible is to take a number that is divisible. So in this case, that's 3 times k. That's a number that is divisible by 3, and then add 1 or 2, and that's due to the possible remainders.
Yeah.
But dividing by 3, okay.
Yep. So so if you're saying that something is divisible by 3, like if you're saying that n is divisible by 3, it's basically actually the same as n equals to 3k or n equals to 3k plus 3. But they still are all the same. Like if you think about this 3k plus 3 and using closure again, that's still like 3 times some variable. So the only possible cases for when determining that if a number is divisible by 3 or not is +1 and +2. And if you have, and if you want to check like if n is divisible by other numbers, just kind of increment like the cases. Okay. Let's see how many minutes do we left. All right. I'm just gonna skip that one. All right. So let's just work on this one together. So this one is also number proof. So we want to prove that 7 is the only prime number that precedes a perfect cube. So this one, I'm just going to use direct proof, but I'm sure you probably can use induction in this case, but I'm not super confident. So we have again, how does the polynomial x cubed minus 1 factor? Or just like kind of like read the sentence, like read the problem. Like we want to prove 7 is the only prime number that precedes a perfect cube. And how are you gonna set up the problem? You know, you're gonna use some variables to represent 7.
So I think if you let, well, I think you just let 7 equal x cubed minus 1, right? That's kind of the problem definition. Is that what you're asking?
Yeah, exactly. So we have the x cubed or perfect cubed. Like we want to prove that 7 is the only prime number that precedes a perfect cube. So we want a minus 1. And we actually want to show that this is equal to 7. And we only have this one answer. So, and we have the hint here. How does the polynomial x cubed minus 1 factor? Just to reduce some time, I'll just write this out. I think is, let me check. I think it's x minus 1 times x squared plus x plus 1. All right, so we can just leave this here for a second. I have another question about the prime number. So what is the definition of the prime number?
A prime number has exactly 2 divisors.
Yep. Yep, that's right. So like only divisible by itself and 1. So like the prime number start from 2 and 3 and 5 and just keep going on. So it actually all can have like a product of 1 and itself, and that's our only product. So if you think about this in terms of this equation right here, we also have 2 terms that multiply together. How does this 2 imply? Or like how does this imply this two term.
You have to set x minus 1, or x minus 1 has to equal 1, and then x squared plus x plus 1 has to equal that prime number, I'm guessing, something like that.
Yep, exactly right. So, but we can also consider that into two cases, where the first case is just, like you said, the x minus 1 is equal to 1. But just don't forget, we can also think about if x squared plus x plus 1 is equal to 1. Let's look at the first case now. So if x minus 1 is equal to 1, and we know x is equal to 2, and we just substitute this back into the equation, we have that x cubed minus 1 is actually 2 cubed minus 1, that's 7. Okay, all right, and see, and you will see, okay, now I think I kind of like showed that this is true. But for the second case, if we just check that if there's a possibility that x squared plus x plus 1 is equal to 1, is there? Yeah, so that's where we probably when x equal to 0. But can x be equal to 0? We actually, so we know that at the start of the problem, we know that x cubed minus 1 is a prime number. And we want to show that the only answer to this is 7. But the prerequisite is that this term is a prime number. Can a prime number be 0?
No, because it can't be divisible by itself.
Yep, exactly. So that basically implies that the x cubed minus 1 term has to be greater than 0. Or in the other words, it has to be at least 2. But greater than 0 is all we need. So we know that x cubed has to be greater than 1. So we know that the second case cannot be actually exist at all. And hence, like the first case is the only answer. So the 7 will be the only prime number. Yep, right. And definition of the primes is that they are positive integers. Yep.
So I wonder, maybe this is too weak, but I'm wondering if just your factorization would prove that x cubed minus 1 would be a prime, because you can't factor the right term any further. Maybe that's wrong though.
Yeah, so basically, yeah, I see what you're saying. So basically, we're just kind of use the idea that a prime number has to be like the two factors has to be one of them has to be 1, and the other one is itself. So we just kind of use this this property of prime number to have the two cases, but our case 2 actually does not exist.
I guess what I'm saying is that if it can only be factored to those two terms, would it be a prime number by definition then?
Yeah, so at the first place, we're assuming that
Oh, I'm just proving that x cubed minus 1 is a prime. Never mind. Sorry, that's not useful.
Yeah, we're trying to show that 7 is the only answer.
Right. Sorry about that.
No, you're good. So any question on this problem? I know like this one kind of like recur like more like thinking about like how the actually logic is going on here. I think we have like 3 minutes past. Sorry about that. You can you're free to go if you want to. And if you have other questions, you can stay and ask anything about like the quiz, the homework, or just general questions.
Thank you.
Have a nice day.
On this question, do we need to do anything further to like complete the proof, or is what we have enough?
Yeah, I think this is enough. Just kind of like add 3 or 2 sentences to kind of explain and just connect all the steps together. To just kind of say that because of something, and then thus we know that 7 is the only prime number, and you will get full credit.
Okay, thanks.
Really quick, we can watch these, correct?
Yeah. You can watch this on the in the playlist.
Okay, awesome. Thank you so much.
No problem.